Alright gang, we got 1.3 and 1.4 of Unit 1 in the same video. Both pretty simple when it comes down to it, you know, at the end of the day. And we have spaces here on the 1.3 part of things and here to draw some pictures, but I'm going to draw them over here. So, but you can use these spaces. I hope it's a big enough space. It should be, to make your picture, you know, not tiny, right? But now we're actually going to start with section 1.4. We're going to do length of a curve, and then we're going to do surface area. So just keep that in mind. We're going to start here on the back of your handout with section 1.4, length of a curve, okay? And I'm going to start with the picture over here. So, I mean, what we're essentially doing is we're going to, you know, see how we can use calculus to give the length of any curve in the plane, you know, where you have the equation for and stuff, you know, or arc length. So length of a curve or arc length. And I only want to emphasize that a little bit because I think if you were looking it up in like the index of a textbook, for example, like I'm pretty sure our current textbook in 2019, you'd have to specifically look up arc length. But actually, now that I'm talking about it, I think if you actually looked up in the index for length of a curve, it would actually point you to, you know, see arc length instead. Like it would actually be in the index, but wouldn't tell you a page number. It would just say go to arc length for a page number. Anyway, why am I rambling on about that? Here's how this works. So just like a region of area that you need to define, and kind of like you know, the volume of a three-dimensional solid, we're going to break this up into a bunch of like mini line segments. And so I'm going to just access my tool here, and I'm going to go with, what would be a good color? I don't know, let's just go with this greenish. So basically, we're going to break this up into, I don't know, what's going on there? Maybe I should use the pen tool instead and just try to draw really straight. Pen tool goes over this other pen. So that straight line, 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 and that straight line. So 1, 2, 3, 4, 5, 6, 7, I believe, like little line segments, diagonal type line segments, usually going to be diagonal, and not vertical or horizontal or anything, but they're line segments, that's the point. And if we added up the lengths of all those line segments, we would get something kind of close to the actual arc length. And again, just like with finding the area by adding up rectangles, or finding the volume by adding up the volumes of discs or whatever, cross sections and areas, whatever. If we were somehow be able to use the integral to instead of doing like 7 line segments, we could do basically an infinite number, and that would pretty much get us to exact arc length. And I mean, ultimately, I guess I'm dragging this out even. I mean, trust me, like I'm going to fast track this. I probably could just fast track it even more, because at the end of the day, this is just going to be a formula that you can just kind of bust out and just use like basically all the time for any problem. But anyway, at least any problem that you're going to be given, you know what I mean? But anyway, how would you describe the length of all these green line segments? And I guess, just spoiler alert here, just cutting to the chase. To find the length of a diagonal line segment in the plane, it's essentially going to be the Pythagorean theorem, won't it? Or the distance formula, which is based on the Pythagorean theorem, and finding the length of a hypotenuse, you know, like a diagonal type hypotenuse, right? So, anyway, here's the punchline. This is just, and again, this is 1-4, not 1-3. But here's a formula, and it just boils down to this formula, where we're going to integrate from wherever to wherever, and it's going to be the square root, the entire square root of 1 plus, and this is the derivative. Whatever the function is, you take the derivative of that function, f prime of x, and you square that derivative, and you put it here in the formula underneath the square root. And I know this might not blatantly look like the result of the Pythagorean theorem, but I mean, you can pretty much see it, you know, the whole like square root of, you know, sorry to use a and b again because it's not the same, a and b, but the square root of a squared plus b squared, or the square root of x squared plus y squared when the hypotenuse is r or something. So you can kind of see how this is coming from basically the Pythagorean theorem or the distance formula. And that's going to be basically something we can use. And man, you know, it's as simple as just using a formula, right? So here's the example problem. Oh, by the way, this is with respect to x, you know, with the function being in terms of x, you know, f of x, and these values over here, a and b, being x values. You could easily write a version of this, and I might as well to make the video fairly thorough, you know what I mean? And the way I believe I was taught in high school and I guess college, probably in college as well, was to call it C and D when it was y values. Anyway, I don't know if I said it already. We could easily write a version of the formula that was like with respect to y, where the function was f of y, you know, basically solved for x. And so you could call the function f of y, and then it would be dy, and these limits of integration would be y values. But it's basically the same thing, you know. dy, but so there's two different versions. It's not two different formulas. It's just two different versions of the same formula. So let's do this example now. We'll just, you know, dx, of course. Find the length of y equals x to the 3/2 power from 1 to 2 root 2 to 2 root 2. Use both formulas, and what that means is, you know, like it basically is saying we could potentially do the problem twice, getting the same final answer, of course, both times. But the first time through, we would use the dx version of the formula, and then we could also use the dy version of the formula instead. And, you know, but let's do the dx version. So we want x values. So what's our limits of integration if we're going from here to here? Well, we're just going to use we only really care about the x coordinates of those points. So we're going to go from 1 to 2. And And then from there, it's just a matter of plugging into the formula. So we have a 1 plus, and then here we have to do the derivative. And so what's the derivative, like what's f prime of x? That's going to be 3 halves comes down, x to the 1/2 squared dx. And you could throw that into your calculator as is, but I don't know, I'm usually the type of person to clean it up a little bit. And so when you square this whole bubble, you're going to get 9/4, and then just x, I believe. Power to a power. Yep. Ooh, where's my calculator? Math Niner. That's, the math button, and it's option number 9, basically. So math 9 to get to function integrate. And let's see here. We got to do the whole square root here. 1 plus, I'm going to put 9/4 in its own set of parentheses because I'm paranoid like that, but I don't think it would be necessary. But again, better to be safe than sorry, and again, it's just paranoia probably, or I don't know, my own quirkiness. So close that square root, comma x, comma 1, comma 2. Close that whole function integrate thing. And it looks like we get approximately 2.086. All right, now on to surface area. Surface area is going to be, again, just ultimately just a formula. But surface area, when you're talking about surface area, you're talking about something that's three-dimensional, like a solid or whatever, that has actually a surface area. So yes, in the surface area problems and stuff, you're going to be rotating about either the x-axis or the y-axis. Again, because it's pretty much just going to be as simple as it's either going to be revolving around the x-axis or something revolving around the y-axis. So the formula we write down, or the pair of formulas we're going to write down, one dx version, one dy version, you can pretty much just use across the board. That formula would work as long as you're just rotating about either the x-axis or just the y-axis and not some other vertical line or horizontal line, okay? But anyway, so this is definitely a three-dimensional thing going on that will give you surface area. So again, it's like we're going to slice the solid up into an infinite number of disks that all have surface area, and we're going to add up all of those infinite number of surface areas, and long story short, too late. That's a classic line from the movie Clue, by the way. Long story short, too late. Now you know. But and look, we can try to get into exactly where this formula comes from and why this 2 pi f of x times this same square root, why that actually translates to, the surface area of just one of these random, surface areas of these disks, you know what I mean? And you know what? To be honest, I probably wouldn't even be the bestest person. I've never 100% quite understood why this part's in there. But I haven't thought about it in years. I just kind of, I just kind of gave up really quickly years ago, even when I was your age, and just was like, well, this is the formula, you know. But so if you want to in class, we could take another fresh look at this together, and I'm sure I could break it down for you if I had to. But for now, we'll just trust in the formula. You know, you can probably understand why there ends up being a 2 pi in there. And this f of x part, you know, just at least doing one part of it, you know, why the heck not? What do you think the f of x part represents from the picture? You know, how do you put f of x into this picture, and what is f of x in this picture? Wouldn't f of x be from the axis to the curve? So that would be the radius. So I'm sure we're going to need the radius, you know, in the whole like geometry of finding the surface area. And so the radius shows up in the formula, you know, here as f of x. So anyway, but let's just kind of go with the formula and just trust in the formula. And by the way, there's also a dy version where I guess you'd be revolving it around the y-axis if you had a problem like that. So you pretty much have to, if your problem has you revolving something around the y-axis. C, D. And again, this is just going to be like all in terms of y now. So it would now be f of y, you know, using the y variable. So you'd have to solve for x if, you know. Just like here, if we were to actually do this problem the other way, we would be using those values, by the way, but we would have to also solve this function for x and end up, I think, with x equals y to the 2/3 power, probably. Don't quote me on that, but let's get back to our problem. And so is this about the x-axis? Okay, so this is around the x-axis. So we're going to use, and these are the x values on the interval, -1/2 to 3/2. And then so we have a 2 pi. We have an f of x, which is just this. Oh man, I might, just in case here, I sense the risk of running out of room. Hopefully you're not in the same boat. So I'm going to move that over. So there's my f of x. Okay. Now comes the giant square root where we do 1 plus, and now it's going to be the f prime of x and all of it squared. And this is where you might want to go off on the side to, maybe you just want to kind of isolate the whole part of it where it's like f prime of x all squared, but I'm just going to do it all along the way here, you know, right in the formula. So, you know, this happens to be, I'm gonna, well, I can probably squeeze this in, how this is really 4 minus x squared all to the 1/2 power. And looking at it like that, just, you know, it's at least a little bit nicer to look at when you're thinking about what the derivative is going to be. And so let's get this started. And so now what's f prime of x? We got to bring the 1/2 down. We're going to have that 4 minus x squared in the bubble. We're going to take that 1/2 down a notch to make -1/2. But we also have to tack on the derivative of the inside with a chain rule and get -2x. The derivative of the inside here is -2x. And we square all of this. Jeez. dx. Woo! Now, if you want to plug all that into your calculator as is, Making sure to throw parentheses in the right spots. Hey, be my guest. You could. But let's see here. Do I want to bring the 2 out front? Let's just bring the pi out in front for now. I mean, I can always adjust it later. And just doing a little bit at a time. Now, what's going on in here? So, if I multiply the -2, well, maybe just the 2. Whatever. -2 times, so it's almost like this times this will be 1, or like -1. But we're squaring this whole bubble, right? So this negative also gets squared, so that's just going to be positive. So I can pretty much forget about this being a minus because we're going to square this whole thing. 2, okay, 1/2. And then this is going to be when I square this bubble, it's going to be 4 minus x squared to the -1 power. So here we go. So this x is going to be x squared to the -1. So basically this x got squared to be x squared, and then this bubble to the -1/2 power got squared, so now the power is -1. Now if you want to, that might be a little bit simpler to throw into your calculator, right? But anyway, you could also theoretically, if you wanted to, because you can do square roots multiplied together. You know, if you wanted to simplify this even more, which you might be cashing out at this point in time, just going, I'll just throw this into the calculator. But square roots can multiply together. So if you multiplied this square root times this square root, you would essentially be multiplying the 4 minus x squared here times all of this, which would mean you'd be like distributing it to the 1 and to this whole thing. And so here we go, man. Okay. So what do I want to write here in the final thing? Well, let's just do the square root, I guess. So 4 minus x squared times the 1 would be 4 minus x squared. Okay? And then when you multiply 4 minus x squared to this whole term, you can multiply 4 minus x squared, which is essentially to the 1 power, times this, which is like the -1 power. You end up with 4 minus x squared all to like the 0 power. And so that's just 1. 1 times this. You know? So essentially, when this quantity, 4 minus x squared, multiplies to this whole thing, you're really just going to multiply it to, in order to simplify and stuff, multiply it to this and essentially get 1. And so you end up with that. Because 1 times x squared is just x squared. And so I'm just about out of space, but this is actually cleaning up really, really, really nice actually, because minus x squared plus x squared, that's gone, and you're just going to be left with like the square root of 4, which is 2. So all of this is just going to basically become 2 times this 2. And so you can essentially just integrate 4 from here to here. So let me just do that. Math 9. So I'm just integrating 4. And yeah, you can just integrate numbers with respect to x. Like it doesn't matter that there's no x I'm plugging in. But it is going to be comma x and then comma negative. I'm just going to do negative 0.5, comma, and then I'm just going to do 1.5 because that's the same as 3/2. 8. So all this just becomes 8, and then with the pi out in front, this becomes 8 pi. And basically, if you were someone that just tried to throw all of this into your calculator at once, your calculator should basically say 8 pi, which if you got a decimal for some reason, like if you put the pi in there with your integral, then your calculator might be telling you 25.13274,123, which approximates to 25.133. But, probably the bestest answer right there. Thanks to Volbeat, Let It Burn, Song of the Day. Heard it for the first time ever today. Love it. And I think that should take care of 1.3 and 1.4. So that video ended up being way longer than I probably thought it might. But basically, because all this really boils down to is surface area. Oh my god, I never finished this? Unbelievable. Talk about getting distracted. And then, whoa. dy, of course. But anyway, as I was saying, like these topics just really boil down to formulas. Surface area, if you're revolving around the x-axis, then you use this version of the function. If you're revolving your region of area around the y-axis, then you use this other version of the formula. And same thing with arc length or length of a curve. It just boils down to a formula. So easy peasy, nacho cheesy. And I think that's where I'm going to call it a wrap.